So in our last two analogies, the analogy of a balloon and the analogy of spring, we found four common steps. Number one is there is initial state to both. Initial state to balloon. For a balloon, it's deflated, and for a spring, it's uncompressed. Uncompressed. The second thing we do is we apply force. We apply force. So for a balloon, we try to force fluid into it, and that fluid could be air, helium, or water. And for spring, we actually just simply apply force vertically on it. So as a reaction to our force, the balloon inflates, and the spring compresses. And the last thing we do is we stop. For a balloon, the stop limit is when we think it might burst. And for spring, we know that it's gonna get fully compressed, beyond which we cannot compress it any further. I want you to just give point 3 a little more attention. So when we apply force and the balloon starts to inflate, basically what we are doing is we are storing fluid in the balloon, and that fluid is basically air, helium, or water. But in case of a spring, so we are storing fluid, and in case of the spring, we are actually storing energy in the form of potential energy. So the more we compress spring, the more potential energy we store in it. And same goes for the balloon. The more fluid we put into it, the bigger it gets, the more it inflates. The size of it becomes large. So now I want to just dive into the capacitor. First of all, I want to talk about what a capacitor is. In electronics, capacitors are used to store charge. And the anatomy of a capacitor is like you have two parallel plates. So I will say this is plate 1, and then there is another plate 2, and these are two wires. In 3D, these plates can look like if you're talking about a parallel plate capacitor, these plates are right parallel to each other and facing each other. These are basically also metal plates. That is very important. Capacitors won't work if these are not metal plates. They have to be metal plates. So let's now talk about how our analogies relate to our concept of the capacitor. So capacitors also have an initial state, that is, we don't store charge on it. They are just empty, just sitting on the desk doing nothing. So let me do it, not charged. Got it? Okay. Second thing is, now we apply force. But what does this mean in case of a capacitor? Okay, so let me show you a little circuit here. So this is our capacitor, two plates parallel to each other, and applying force means that you put a battery right here in parallel with the capacitor. So this is the negative end, this is the positive end, and then you connect it right here. That's what you mean by applying the force. So apply force basically And this force basically says, hey, all the free electrons on this end of the plate, I'm attracting, they get attracted to this positive end of the battery, and all the free electrons in this wire and this plate gets pushed away because they are getting repelled by this negative end. Okay, so that is our second thing, which is pretty much, force, I will say force charge imbalance. Because before connecting the battery, the capacitor was neutral, but now as soon as you apply the battery, you are forcing the charge imbalance. So that is our second point. Number third is, as a reaction to your force, the capacitor starts getting charged. The capacitor starts to get charged. So what I mean by that is that, so we know there are a lot of free electrons right here on this plate, and there are also same number of free electrons, maybe more, on the other side of the plate. No, they cannot be more because it's neutral, so they have to be at the same. So these free electrons gets attracted to this positive end of the battery. So now we see the fluid of these electrons. I'm calling them fluid because, believe it or not, in 19th century, electrons, the movement of electrons was considered fluid. But for in order to be very close to my analogy, that's why I'm calling them fluid. But so let's say these are charges, negative charges. Electrons are negative charges. They are now flowing to the positive end of the battery. The similar effect is happening on the negative side of the battery. That is, all the free electron in this wire and this plate gets repelled by this negative. So now the charges move away from the other side of the battery to the positive, to this side of the plate. So with the passage of time, what's happening is that this plate is becoming more and more negative, and this plate is becoming more and more positive. So this is the reaction to our force. So what is the fourth point now? So you stop. So, but the thing is, with capacitors, they stop automatically. So what's happening is that when this plate becomes enough positive or equally positive to this end of the battery terminal, so the electron won't move anymore, because they say that they're being attracted to both sides, the plate and the positive end of the battery, equally, so they just stay where they are. And that's where we say that they automatically stop, or the process stops. Or we can also say that the capacitor is now fully charged. The capacitor is now fully charged. So what happens next? We have two options. We can remove the battery and the capacitor will stay, an ideal capacitor will stay charged forever. Or what if we want to discharge this capacitor? In case of the spring or the balloon, we will let the balloon go and the air or the fluid will come rushing out. Or with the spring, we will just remove the force and the spring will pop right back up. But with the capacitor, the awesome thing is that even if we remove the battery, which is the force, the charge remains on the plates. So that means that our capacitor is charged, and that's why they are so useful. But what if we want to discharge them? The only thing, the crazy thing, the easiest thing we can do is we can remove this battery and just short circuit this plate or this side of the capacitor directly to the other side of the capacitor. Just short circuit it, and what will happen is that the electrons will see this happening and they will say, hey, we want to go back to the way we were, and they're gonna go rushing back to their original state. So that's what we call the discharging of the capacitor. And sometimes this discharge is very violent. I mean, most of the time it's very violent. When I say violent, that means that all the charges wants to get back to where they were at once. And that will bring us to our real life examples of capacitors in Mother Nature. So the next would be that.